At this point, we've talked about the derivative. We've talked about some of the properties of the derivative and some of the basic rules of how to find the derivative. We've talked about the derivative of constants. That would be 0. We've talked about the derivative of constant multipliers. With those, you can actually just put them in front of the derivative. And we've also talked about the derivative of sums and differences. Those didn't seem to be much trouble. You just take the derivative of each term separately. So now that brings us to products and quotients. The derivative of a product is not as easy. It's not what we would like it to be. Let me demonstrate what I would love the derivative of a product to actually be. This is section 2.3, and it's the product and quotient rules. Now, if you were to take the derivative, d dx being the verb, action verb, take the derivative with respect to x, of two functions multiplied together. Wouldn't it be great if the derivative worked for products like it does for sums? Unfortunately, it does not. What we would love to happen would be that we simply distribute the derivative and we say, well, all we need to do is take the derivative of the f function and multiply that by the derivative of the g function. In other words, f prime times g prime. While that's what we would like, that's not the way it works. Now, I can demonstrate to you that that does not work by doing the following. I'm going to take the derivative of this product. Now, let's not use any rules at all. Let's just multiply them out. This is x squared minus 3x plus 2x minus 6. This is the derivative of x squared minus x minus 6. We don't need any special rules for this. So what we're going to do is simply take the derivative of our power. We're going to take the power down and deduct 1 from that exponent. Minus 1 is a constant multiple, so that doesn't go anywhere. So we only have the minus sign, but the derivative of x is 1. And the derivative of minus 6 is 0. This is the correct derivative. And it's a function. Let's say for a moment that the derivative of products was as easy as we would have liked. If it was as easy as this, then we would simply take the derivative of x plus 2 separately, and then over here, take the derivative of x minus 3. Well, that certainly can't be true, because the derivative of x plus 2 is 1, and the derivative of x minus 3 is 1, and the answer is 1. So no, it does not work. So there must be another rule at play here, and there certainly is. So we're going to talk about the product rule. Now, I'm not just going to give you the product rule. I want to show you how we figured out the product rule, and then let's retest the product rule on this very problem to make sure that it's working properly. So, let's say I asked you to take the derivative of a product. Using the limit definition for derivative says it's the limit as delta x approaches 0 on this big function evaluated at x plus delta x minus this function evaluated at x all over delta x. So let's take this function evaluated at x plus delta x minus, let's take this function and just evaluate it at x. And that should be all over delta x. That is the limit definition of the derivative. In fact, where did it come from again? That actually is a rise over run. It's actually the slope of a secant line. But then we take the 2 points closer and closer and closer together, and that's why delta x is going to 0. So that's how we originally found the derivative. Now, if I were to go in here and add a couple of terms. Now, you might not think of adding these two terms, but I can, if I want to, add and subtract the same quantity in here and not affect the numerator. I could add 4 minus 4. I could add x minus x. That's 0. It doesn't affect the actual quantity, the original quantity. So again, you might not have ever considered to do this, but let's add and subtract the same item. And so this will be way in the back here. So let's subtract and add some quantity that will help us figure this thing out. Now the quantity that I'm going to add and subtract actually is going to be the f of x plus delta x times g of x. And if I'm subtracting it, I'm going to have to add the exact same thing in. X plus delta x times g of x. So I know it's pretty ugly and you wouldn't consider doing that, but just check it out. Plus the same quantity minus the same quantity, they really do cancel out. So you can always add and subtract the same thing if that's what you want to do. In this case, that is what I wanted to do. So now I'm going to do a little grouping here. I'm going to redo this limit like this. I'm going to put these two together. And it does get a little messy here, but it will give us what we're looking for, which is going to be the product rule. And then over here, let's put these two together. Well, all of a sudden, we do have the limit of a sum, and we certainly like that because the limit of a sum, you just do the limit of each term separately. So let's do the limit of this sum. Not only do we have the limit of a sum, check this out. On this particular set of terms, there is a common factor. So let's do the first limit, which is this one. Rip the common factor out. And then in parentheses, show me what's left. So that's this first limit right here, this big messy limit here. Now we have a plus, and the limit actually comes over and distributes, and now we're going to apply it over there. So it says plus, the limit distributes because it's addition, and now, oh, there's a common factor over for these two. Look at that. G of x can be factored out. So let's take g of x and factor it out. In parentheses, show me what's left when you remove these two. So, now limits are different than derivatives. Limits distribute so well that they actually also distribute to factors. So this limit can be applied just to that. And this limit can be applied to that whole package over there. Let's do that. Same thing here. Distributive law, in a sense, for the limit. It works for products, too. This limit can apply just to that, and this limit can apply just to that. So let's write out what we have now. Separate limits here. So limits are different than derivatives. Limits actually will distribute through multiplication. So why did we go through all that? All of that was legitimate. All of that was allowed, and here's why we did that. First of all, let's execute this limit right here. Let's literally send delta x to 0 with direct substitution, and this is what you get over there. That's just the f of x. And what is this thing right here? Well, that's the very definition of the derivative, isn't it? It's g prime. So we'll write g prime next to this. Plus. So what's this? Delta x goes to 0. G of x doesn't care about that. There is no delta x in there. So it's just g of x. And what's this right here? This is the very definition of the limit. So after all that work, what is the product rule? Well, apparently the derivative of a product is not just f prime times g prime. It's, and I'm going to put this in a different order. I can use the commutative rule of multiplication and addition. It's f prime multiplied by the g function plus it's f multiplied by the g prime function, the derivative. So let me summarize that for you. F prime g plus fg prime. So remember, when we started this off, we were very hopeful that we could have a nice shortcut like that one, f prime times g prime, like a derivative distributed through to each of these. That was not the case. This is called the product rule, and it's a rule that we need to know. We see this a lot in calculus. So I did say I would go back to the original problem to see if it worked. If you remember, we took the derivative of x plus 2 times x minus 3. And because we didn't really know the product rule, we actually went ahead and multiplied the contents to learn what function was in there first, which was x squared minus x minus 6. At this point, we can use the power rule, the constant multiple rule, and the constant rule to come up with 2x minus 1. That is the correct derivative. So now, I'm going to label this. I'm going to label this as f. I'm going to label this as g. And let's see if we can work this through with the product rule and get the same result. So you do have the derivative of f of x times g of x. And the product rule states that the derivative that you seek right here, you should be able to find it by doing f prime g plus fg prime. Let's see if that works. Well, great way to do this is make a table. So you have f, just x plus 2. You have f prime. Okay, f prime is just 1. You have g, which is x minus 3, and g prime, which is just 1. So now you mix and match them together, like this. F prime times g plus f times g prime. That's x minus 3 plus x plus 2. Well, I see 2 x's, and I see a minus 1 right there. Pretty amazing. It matches up. So the product rule, very successful way of finding a derivative. So again, the product rule is different. We can't just distribute the derivative to each term like we can with addition subtraction. With a product, you can't just do f prime g prime. It's f prime g plus fg prime. Now notice there are two functions. Product rule has two terms. Each term has two factors, f and g. And what we end up doing is rotating the derivative through that. Two functions, two terms, each term, two factors, the two functions themselves, f and g, but we actually rotate the derivative through. So we do f prime here, and then we do g prime there. Now, how does that translate into a derivative of maybe more than two factors? Like, what if we wanted the derivative of three functions? Like that. Three functions, and we want a derivative. Three functions, three terms. 1, 2, and 3. Three functions, three factors. And rotate the derivative through. So this one will have the f prime, the next one in the middle will have g prime, and the last one will have h prime. So using the product rule you can effectively take the derivative of much larger products if you need to. Let's apply the product rule to a problem where we can't take the derivative using our previous techniques. The first one we did, we could actually take the derivative using the power rule, the constant rule. We actually multiplied it out. But here's an example where you can't do that. There's no way to really multiply that out algebraically and then take a derivative. So, first thing you want to say to this is it is not what some people think it is, which is the derivative of x and the derivative of sine. It is not cosine. We got more work to do here. This is my f function, this is my g function, and now we've just learned that the derivative should be f prime g plus f g prime. Now, best way to do this is to make a table of your functions. And I mean f of x, but we just shorten that up to f prime. The derivative of x is 1. G function is sine. G prime is cosine, of course. Derivative of sine is cosine. Let's not forget, the derivative of cosine is minus sine. And let's mix and match these together. So f prime is 1. G is sine. F is x. G prime is cosine. So the derivative here is the sine of x plus x cosine of x. Pretty tough to get without having a product rule. So make sure that you know your product rule. Now, the next thing I would like to introduce is the quotient rule. For sums and differences, we have a sum and difference rule. That's a pretty common sense rule. You can literally distribute your derivative to each term separately and then just take the derivative of each term separately. Now for products, we have a rule. F prime g plus f g prime. You can't just do f prime times g prime. There's also rules for quotients. And again, it's not as straightforward as it is for addition and subtraction. So let me see if we can reason out what would happen here if we were to take the derivative of a quotient. You know what we can use here, guys? The product rule. Now, that's not a product, but it will be shortly. We all remember negative exponents. Negative exponents mean I belong on the other side of the fraction. I belong down here. So this has now become a product. I know it's a quotient, so apparently any quotient can be written as a product. And what I'd like to do is just try to run the product rule on it. And it looks something like this. Now, we're going to just call this the f from the product rule, and we're just going to call this whole thing the g from the product rule. And the way the product rule works is that ultimately we need to mix and match these together as f prime g plus f g prime. But the f in this problem is truly f of x. There it is. F prime is f prime. It's the derivative of that function. The g for the product rule is the whole thing here. So it's actually g of x raised to the negative 1. Now, in order to do this, I have to use a rule that we have not really gotten to yet called the chain rule. So for now, you're just going to have to accept it. Later, you'll see that what I'm about to do here is correct using the chain rule. But at least for the exponent, I think you realize that if you were to take a derivative of something to the minus 1 power, which I'm about to do, what are the rules for exponents? Well, exponents love to come out front, and then we deduct 1 from our exponent. Normally what's inside actually doesn't get changed. And right here, this is the only thing you don't know about yet. I've taken the derivative of basically the exponent portion of the problem, and then a chain rule actually puts another derivative which is the derivative of the function itself, and that would be, in this case, g prime. So that's one you're just going to have to accept for now. Later, when we learn the chain rule, you will see that it is correct. Let's put this together. F prime is F prime. G is the old function raised to the minus 1 power. That's F prime G. Now plus F. Well, that's F right there, F of x. Times G prime. Well, that would be times -1, the original function to the -2 power, and you get a G prime on top of that. That comes from the chain rule. So that's quite a bit over there. Now, let's see what we got over here. This is F prime over G. The -1 says, put that at the bottom of the fraction. Now, this is a positive times a negative, so that's negative. Here's my F of x right there. Here's my G prime. Nothing wrong with that. It doesn't belong anywhere but the numerator. And look at this, -2 as an exponent. That says I really belong down here. Now, you want to get these two fractions to go together, and the best way to do that is to multiply by g of x on the bottom and g of x on the top, and I think we just discovered the quotient rule. It's F prime G minus F G prime all over G squared. It's the same thing. So this we refer to as the quotient rule. So the quotient rule produces a quotient, first of all. And the second thing is, now we know why that g squared is down there. Oftentimes people ask me, where did that come from, that g squared? It actually came from a derivative. G prime, you got the -1 to drop down, and then the exponent was deducted, became -2, so it ended up down in the bottom. So let me summarize the result here. The derivative of a quotient, f of x over g of x, is summarized as f prime g minus f g prime all over g squared. So how do we remember this? Well, I like to remember this pattern, alphabetical order, so f and g. So it's going to be, product rule is f prime g plus f g prime. You notice that I primed the first one. That's the product rule. Quotient rule is the same order, except with a minus. So it's f prime g minus f g prime. And it also has that additional g squared on the bottom. Let's try a couple of examples. So find the derivative of this function. So if it's a quotient, wouldn't it be nice if you could just say the derivative is 2x over 2, the derivative is x? I wish that were the case. You can't do that, so you need the quotient rule. Very carefully apply it. What I do is normally label these. There's my f and my g. I also make a table. So f is equal to x squared minus 3. F prime would be 2x. G would be equal to 2x plus 1. G prime would simply be 2. And let's get to our derivative. It is, again, f prime g minus f g prime all over g squared. So for my problem, f prime is 2x. G is 2x plus 1. F is x squared minus 3. G prime is the number 2 all over g squared. couple things about this. Number one, do not cancel this with that. The reason you can't do that is because of that minus sign. Pluses and minuses out in the open like that prevent you from doing any cancellation at all. So no cancellation. What I do want to do on the top, though, is I want to simplify what we have. So let's do our distributive law here. That's 4x squared plus 2x. Let's do our distributive law here. So that's going to be a minus 2x squared. And a minus times a minus is positive 3 times 2 is plus 6. We could square that out if you would like. But I'm going to leave it like that just for the moment to see if there will be any cancellation. Or maybe write the two factors out like that. So what do we really have? Well, 4x squared minus 2x squared is 2x squared plus 2x plus 6. Now, this is a point where you might be able to find some cancellation. Let's see if we can. The way to cancel, you really want to factor and cancel, and there is a common factor, which is 2. But this is not factorable here. That's not a factorable quadratic. So at the end, maybe we'll put it back together. You always factor to see if you can cancel, and then you actually can put it back together. And also, let me show you what we have down here. This is 4x squared plus 2x plus another 2x, so that's plus 4x, and then 1 times 1 is 1. So there's our derivative right there. So you can see you can take the derivative of quotients now. You need the quotient rule, f prime g minus f g prime all over g squared. Product rule, f prime g plus f g prime. Now I want to show you something. We do know the derivative of sine and cosine. I mentioned it earlier. The derivative of sine is cosine. The derivative of cosine is supposed to be minus sine. We don't know the derivative of tangent yet. We haven't talked about that one. Can we discover the derivative of tangent by only knowing the derivative of sine and cosine? Now, we could certainly look it up. There's a derivative table in which tangent appears, but why not figure it out on our own? Because tangent can be written as sine over cosine. And if you do write it as sine over cosine, look what you found. A quotient. Label this as f, label this as g. So f would be equal to the sine of x. F prime is the derivative of sine, which is cosine of x. G would be equal to cosine of x. G prime is the derivative of cosine, and remember, that's minus sine. Let's not forget how to mix and match these together with a quotient rule. It's f prime g minus f g prime all over g squared, and simplify as much as we can. F prime, right there, cosine. G, also cosine. Minus f is sine, and g prime is minus sine. All over g squared. Let's take a close look at what's on top here. A negative times a negative is positive. Sine times sine is actually sine squared. Plus, cosine times cosine is cosine squared. And this just is cosine squared right here. But by the Pythagorean identity, isn't it true that sine squared plus cosine squared of any quantity is equal to 1? And in fact, we can make it even simpler than that. If I package this up as 1 over cosine and square it, 1 squared is 1, cosine squared is cosine squared, we have a name for this thing. It's called the secant. So interestingly enough, the quotient rule not only will get you the derivative of quotients, it actually gets us the derivative of some of these trig functions, like tangent, for example. It'll do the derivative of other trig functions like secant and cosecant and cotangent, because they're all fractions too, okay? And they're all fractions that involve the use of sine and cosine. So You should be able to get all of those as well. That one's an important one, by the way. That means I do want you to remember that the derivative of tangent is secant squared. We need to add that one to our knowledge base. That's important. Okay. Now I want to talk about when not to use the quotient rule. We just learned the quotient rule, and now I'm going to tell you not to use it. So when do we not need it? Now, if you use the quotient rule and you use it correctly, it should lead you to the right answer, but sometimes it's overkill. Let me give you some examples. No doubt that that is a fraction. No doubt that the quotient rule will work successfully on this. But why waste your time? Because 2 is simply a constant multiple that deserves to be out front. Okay, that's fine, but you still have a fraction, and the only way to take the derivative of a fraction correctly is to use the quotient rule, and that is correct. But can't you just push this to the top? And won't it just become x to the minus 2? And you don't have a quotient anymore. You can just take the derivative the regular old-fashioned way. The regular way of taking the derivative with the power rule is you check this off. The negative 2 will come out front. And the derivative then will, be careful, deduct 1 from the exponent. Now, when you're all done, we don't really like negative exponents in a final answer, so you're able to pick this up and put it back where it belongs, down on the bottom. Will the quotient rule work on a problem like that? It absolutely does work. Is it more complicated? Yes. It's more prone to error. If you have a constant multiple, slide it out front. If you just have a denominator on the bottom to some power and there's nothing on top, just push that whole thing to the top. And now you've got a derivative on one line. It's no longer a fraction. So that's the kind of thing we really want to look for. Let's take a look at a couple of other problems here like that. So take a look at this thing. Take the derivative of, let's say, negative 2, how about 2x minus 4x squared all over x or something like that. A lot of work. Now, really, the way to do this is the top numerator would be f and the bottom would be g, but even the top has a product right here, and maybe you need the product rule f times g up there for that derivative, but in reality, that's just a constant multiplier, and we always know what to do there. We can just bring that out front. In fact, there's a common multiple in here as well, isn't there? So before I bring that out front, let's do this. Let's factor this problem. There's a common 2. Bring it out front. Show me what's left. Oh, wait, there's an x as well, isn't there? So if you rip the 2 and the x out of here, by dividing it out, you're left with a 1. Minus. If you rip the 2 and the x out, you're left with a 2x. And look what just happened. First of all, these x's canceled. And secondly, the minus 4 can come out front. So let's do a negative 4 as a constant multiple. And the only thing you really need to take the derivative of is right here. Let's see what that's worth. Negative 4 sits out there and waits for the answer. The answer will sit in here. Now, the derivative of 1 is 0. The derivative of minus 2x, well, minus 2 is a constant multiple. That will not vanish, and the derivative of x is 1. So this is negative 4 times negative 2, and the answer is 8 doesn't even have an x in it. So this is just a good example of, trying to simplify things, rewrite them, factor them, cancel them, and that will save you from a lot of work. You don't need the quotient rule on that. 2 more quick examples and we'll finish up. Let's do the derivative of 2 over 3x to the 4th power. Well, the 2 and the 3 is really a 2/3, and it can just sit out front. Just sit out front in front of that derivative, wait for later. It's a constant multiple. I say they're along for the ride. Now, what about this? You could push that to the top, and it's just simply the derivative of x to the -4. That's just x to the power. So the 2/3 is along for the ride. The -4 will drop out front, and don't forget, deduct 1 from the exponent. -4 minus 1. So here's what I've got here. -8 on top, 3 on the bottom. And can't we pick this up and put it on the bottom, and it will become an x to the 5th power? There's our derivative. No quotient rule needed. Now, if you want to run the quotient rule, you can. I'm not saying that you can't. It's just a lot easier to rewrite it if you're able to do that. One more example. What about this? Very similar problem with a very different result. Now, there's a temptation maybe to pick this up and bring it to the top and maybe look something like this. I wouldn't recommend doing that. I don't think that's going to lead you to the correct derivative. What I recommend doing is notice that this 4 applies to both. I want you to distribute that out first. So it's actually 2. It's 3 to the 4th power and x to the 4th power. In fact, 3 to the 4th power, that's 81. And once again, all we really have is this constant multiple of 2 over 81 that can come out front. And now you can push the variable to the top. I recommend pushing just the variable to the top, not these numbers. These should come out front. Okay, let's finish up. Take the derivative by doing what we normally do, which is take the exponent, bring it out front, and deduct 1 from the exponent carefully here. So this would be -8 over the 81, and this drops down to the bottom again. So I hope I've given you a good guide for using the product and the quotient rule. The best way to get good at it is experience, and that means you got to do some problems. You can use CalcChat if you want to see the step-by-step solutions. If you're having any trouble matching up your answers to the correct answers, which are also in the back of the book, definitely send me an email, get in contact with me, tell me about it in class, and I'll help you through it.